All right. Oh, awesome. That's better. Okay, so last time we were playing with this closest thing a little further. We'll drop it for now. I think there's probably room for some further improvement, but we went down from 2.5 minutes to, was it 250 milliseconds, I think, in user space. We probably need to work on the kernel side of things. That's still single-threaded. Maybe we'll take a revisit that later on. Today I wanted to take a closer look at Pthreads, basically the programming model, some of the primitives that we need to be aware of, and maybe try to put it to the microscope a little bit and see what's really going on. So, like I mentioned last time, threads, that's really the only way that you can make use of multiple cores. That's what it's really for. Then you can argue whether, on a single core, you can argue whether you should be having a multi-threaded programming model or you want to use an event-based programming model. That's a matter of preference, but if you want to use multiple cores, you have no choice. Yeah.
Processes?
Yeah, so if you want to have multiple cores in one program. Yeah. So multiple processes, yes, they use different. They also use threads in the same sense, really, but they have different address space. But that's right. Yeah, you can run multiple processes and you don't need pthreads for it, but you still need threads. So task parallel programming, that's really the only way. We played a little bit with OpenMP in the past. That's for data parallel programming. We'll see that closer later on. Data parallel programming inherently relies on on thread parallelism under the covers. But it can make life a little easier. If you want to, say, slice up a for loop among lots of different threads, then that's data parallel programming. It's really great. Task parallel or thread parallel programming is more a question of, oh, you go start doing this thing, and then you go do that thing, and they're relatively asynchronous, at least if you don't explicitly tell them that they need to synchronize. Each of these threads, they have their own state, right? They're running on a hardware thread in the CPU, so they're maintaining all their register values, or that is, whenever the kernel puts a thread to sleep, it stores all the register values somewhere in a little buffer, and then when it wants to wake up the thread again, it restores all those register values, jumps to whichever instruction you were executing at the moment, and continues running. So it appears to a thread appear to be running continuously. You don't really, from a, I don't know what the right term is, but in terms of just behavior, it seems to the thread as if it owns the CPU. You start lots and lots of threads, all running on one CPU. They all still kind of look like they're all running on their own CPU. That's the intent. Of course, once you start measuring performance, you can tell that that's not the case. Okay, so this is done context switching using timing inruns. So yeah, there's actually a couple different ways you can do this context switching. Of course, the process itself can make a system call, and once you're in the kernel running kernel code, now the kernel can decide, oh, let me stop running that user process, I'll switch to a different one for a moment. But the kernel isn't actually running when the user program is running. That's always the case, at least on a single CPU or a single hardware thread. You're either running user code or you're running kernel code. So the kernel can't observe what the user is doing as the user is doing it. So it's not possible for the kernel to stop the execution of a user program and start running a different one. So what we do to make that happen is we rely on an external timing circuit that triggers an interrupt whenever, or at regular intervals. and then interrupt handling is always in the kernel. So now the user program was running, a hardware interrupt happened, that moves control to the kernel. So now we're running some kernel instructions, and now it's up to the kernel to decide whether it wants to continue running the user program it was running or switch to a different one. So with the timing interrupts, oops. It is called preemptive multitasking. The other one is called cooperative. So if you were to not have a timer interrupt or an equivalent available to you, you could rely on cooperative multitasking, where the thread has to basically tell whether it's the kernel or a user space scheduler that, okay, I've had the CPU for enough now, let someone else run for a bit. You could do it that way too. Cooperative multitasking is it's unreliable in the sense that if you don't trust whoever wrote the other threads on the system, then you might end up with them hogging the CPU forever and you never get to run. Or in the sense that if you don't trust yourself to actually make calls frequently enough to say I'm done with the CPU on one thread, then one of your threads that you wrote might end up hogging the system and the rest of your threads don't get to run. So preemptive multitasking is nice, but it's kind of expensive. The way it typically goes is you have a 10 millisecond intervals, or sometimes 1 millisecond I've seen. So you could imagine if you have 1,000 processes running and you have one core with a 10 millisecond interval, it's actually 10 seconds between runs for each process. Right? If they're all trying to use the CPU, each one of them will get to run for 10 milliseconds, then comes the next one, then comes the next one, and there's 100 of those intervals in 1 second, so it'll take you 10 seconds before the last process gets to use the CPU a little bit. So that can be inconvenient, depending on what you're trying to achieve. Right? If you're just bulk processing, you don't care. But if you care about latency, it might be an issue. Yeah?
What is the term GIL lock in Python?
Sorry, what?
GIL lock.
Interrupt.
Yeah.
Interpreter lock. Yeah. So Python is very many layers above this. Python, as far as I recall, is essentially a single-threaded language. And so they're fine with having an enormous one lock for everything. Perhaps it has to do with signal handling. I don't know why you need locks at all in Python, but yeah, that's definitely not at this level. Right. So that's not interrupt. It's interpreter, like the Python program that interprets the program that interprets the Python language. All right. Yeah, but of course, if we only have the one CPU, what are you going to do? I mean, you have 1,000 threads sharing it. They're going to get 1,000 each of the CPU, which isn't a lot. But it might be nice if they could get shorter intervals, because even 1 millisecond is a lot of time. Like that's on frames, the machine we usually run on, it's 2.2 million cycles. And each one of those cycles, we ought to be able to run between 1 and 5 instructions, so that's really a lot of instructions. Anyway, if you do it more frequently, you end up incurring lots of extra cost for all these switching instead, so you use more time for overhead than for your application, and it's a bit of a trade-off there. All right, but so anyway, well, actually, maybe I should finish along that line. So if you were to run lots and lots of threads on one core, it's not going to work great for several reasons. But basically, you're going to hit some of this if you have some threads that are CPU hungry, they would use up 10 milliseconds, and during that time, no other thread gets to run. If it's I/O, it's a little bit better. Like if they're all doing lots of socket communication, every one of those reads would be blocking probably, and you could switch there. But there's lots of overhead in all this switching. So that's why you may have seen that event-based programming is more popular these days. Maybe you've heard of. Yeah, but then if you care about performance, you would never ever touch Python.
UVLID. I think it's called UVLID for C.
Yeah, I'm not familiar with that one. I was thinking of Node. This is this JavaScript thing. Again, if you really care about performance, you probably shouldn't be playing with JavaScript either. But it is certainly a whole hell of a lot faster than Python. So there's different ways to look at it. Probably for a networked program, at some point you don't care so much about the CPU performance. You care more about the network traffic and handling network traffic as it comes quickly. So I wouldn't say you should write every program in C. That's usually a mistake. I think if it's a program that really needs to go fast and it's a small piece, write it in C. Sometimes even write it in assembly if it's really worth it, right? Or maybe buy 100 more machines. It depends.
So, speaking of cooperative multitasking, Go comes by default. In Go, you have cooperative threads. You don't have access to direct OS threads. So that does cooperative multitasking by default, and that seems to be working really well for the language in the network space because it's mostly I/O based.
Yeah. So Go is in that domain where you mostly are waiting for network traffic, and you don't want to be switching between lots of threads. If you do need to maintain lots of threads from an application logic perspective, then user-space threads, which is what they do in Go, which you can easily do in C if you want it, or in many other languages, can be a good choice. Another good choice is event-based programming. Can get a little hairy, depends on how many rounds of interaction you have with the user before you're done with a task, let's say. Anyway, yeah.
Just a quick question. Yeah. So, say in some scenario where you have like a core that's running just a single thread, is it just going to keep interrupting the same thread and then coming back to it? Yeah.
So if you have a CPU-hungry thread in this case that's just using the core, and no one else is there, the timer interrupt will go off every 10 milliseconds. The kernel will realize there's nothing else to do and go back. If you didn't do this, then there wouldn't be a way for the OS to kind of start a new process on this CPU and things like that. So you do have to yield a little bit of the CPU time to the kernel. It's 10 milliseconds. That's 100. Now we're talking about crazy number of cycles, right? It's 20 million, 100 million instructions, this sort of thing. So I wouldn't worry about that. Some people are under the misconception that if you run kernel code, it'll go faster. That's generally not the case. You would you could avoid this interrupt. You can just disable all the interrupts, and then you don't have to worry about them. But generally speaking, kernel code doesn't run any faster than user code. It's the same story. So you want to write user code as much as you can, because kernel code crashes your whole machine. And it's really annoying. As you may have noticed in 385, or the 461 now, the OS class. All right, so anyway, that's a lot of asides here, but the general idea is this thread appears to be running continuously, and only when we start measuring performance or timing, do we get some sort of better idea of what's actually going on. So there's a few primitives that we need to be, let's call them primitives, that we need to be aware of. There's pthread create to start a thread. So you give it But what's really important is the function to run. Right. I won't write out the whole, all the arguments here, but basically pthread create starts running a new thread, which could be running on the same core or a different core. It could change over time which core they're running on. But basically we're telling the OS that now we have two sets of register contents that we will be switching between, or potentially running at the same time if we have multiple cores. You tell it which function you want it to run. So the new thread will be running this function. And then immediately, well, potentially immediately after you run this pthread create, the current thread just continues executing. Or potentially, it'll go to sleep, and the new thread is what's getting run. This function to run is running instead. Hard to tell. The only way to see on your current machine is to basically check some timestamps and see which one ran first. And then there's no guarantee that it will be the same next time. We just know that these things run in parallel. But you do know that this function to run doesn't start running before the main thread calls pthread create. Right? We've talked about all this speculative execution and that sort of thing. That applies at the single core, single thread of execution level. That sort of weirdness doesn't happen here. Right? Here it's perfectly predictable. What's it called? Causal. Right? Okay. What was I going to do here? I don't know. Put something after. Okay, so pthread join. I guess we need to have a. Let's do it like that. Waits until this other thread has finished running. Oh yeah, and that leads us to pthread exit. Okay, so pthread exit, that's for the new thread to say I'm done executing. Alternatively, you can return from the function to run, and that will automatically call pthread exit. And then there's pthread join. That's for a thread, generally speaking, for a thread that created another thread. The main thread creates a thread and then calls pthread join to wait until that thread is done. Right. There's actually also a return value that you can pass through pthread exit. You can pass a void pointer back from the child thread to the parent. It comes back through pthread join. We don't need to worry about that now. So one common way of doing task parallel programming is you start your main function, and then you find, oh, I need to do all these different things. I can do them in parallel. You start a pthread for each one of them. So now they all run in parallel, and then you do a pthread join, waiting for them all to finish. Pthread join on each one of the threads that you ran. This is called fork join parallelism. It's very simple. You know, you get to run 5 things in parallel, and then when they're done, you run one thing again. And so you would often find this in concurrent programs. You have a serial program. When you don't worry about performance, it's just serial, and then there's some task that needs to be parallelized. So now you would fork out. The pthread create actually uses the same system call as fork for creating more processes. You could do it with processes. It's easier to do with threads. So now we spin out lots of threads for a little while, join, and now we have a single one, and we don't need to worry about concurrency again. That's a pretty nice way to do things. Another way that we can, so that's one way to synchronize as well. You could call create maybe a synchronization function in a sense, in some pseudo sense, like we're starting a new thread and that thread doesn't start until we've called pthread create. Pthread join is definitely synchronization in the sense that the calling thread doesn't continue running until the child thread has called exit. So there's a direct, it's called a happens before edge. You might encounter this, so let's define that. So there's one between, so join creates a happens before edge. We know that whatever happened before, let's see. We know that the call to thread exit happened before join finished. So now you have two different threads executing in parallel. We don't have any idea of the ordering, but suddenly there's one thing here that says this main thread, anything that's after the join, actually happened after everything that happens before the thread exit in the previous thread. Maybe I should draw this. You know, it might seem most of these things are kind of intuitively obvious, but then you start looking in a little bit more detail at it, and you have 50 threads that you're thinking about at the same time, and suddenly it's just a mess. You can't just intuit about it. Sometimes it's a good idea to have a little more formal idea of what's going on. Okay, so, oops. So let us call this a sequence of tasks, a sequence of operations running within one thread. And here's another one. Now these are just some arbitrary order. Now we don't know, actually, let me see. Can I spread this? Let's try that. Yeah. Okay, so we'll make these some color. Where's my fill? Damn it, I can't see it. Is there no fill color? No, there. Okay. Okay, cool. All right, so we have our thread 1 and our thread 2. They have a bunch of, let's call these instructions. Doesn't really matter what they are, but call them instructions. So if they're running on a single core, actually, instructions is no good. Call them larger chunks of work. If they're running on a single core, they might end up like this, right? If this is 10 milliseconds of work, 10 milliseconds of red, 10 milliseconds of white, and so on. If they're running on 2 cores, then of course they're running in parallel, but that's only true if they're operating on completely independent pieces of memory. Then we don't care. These are completely independent parallel operations, these. Now, if they start writing to memory, right, so this piece writes to the global value A, and now this piece reads from the global value A, then it starts getting really important which order things happen in. So what happens before edge is one of these edges that say join. Okay. So if you have a happens before edge between this block here, which has a thread exit in the end, actually then this would have finished like that, then we know that all of these executions, whatever we're doing over here, will be happening after everything that happened over here. So we know that if we read, say, A over here, and we write A over there, we are guaranteed to get the latest value of A. Whereas if you read A here, there's no telling really what's happening. You can get either value. Okay, let's go back to this. So there's many other happens before edges. Almost all of them have something to do with an atomic operation in the CPU in order to guarantee this relationship. Okay, so next up, we want to do some synchronization. Who knows any synchronization operation that we might want to use?
Barrier?
Barrier, yeah. Lock, right? There's one more common one.
Comparison.
Nope,
No, that's not.
that's an atomic operation. Right, a lock and a mutex is the same thing. A mutex. Semaphores are actually more of a textbook construct that you almost never see in reality. They make for really cool puzzles, and I think that's usually attractive when you write a textbook, so that could be it. The one I'm looking for is condition variables, which are really important. So let's look at each one of those. So we have a lock, a barrier, and a condition variable. And then I want to put one more, and we'll call that ad hoc synchronization. Ad hoc just means we're not using pthread functions. We come up with something on our own. Like maybe we write to some value and see if it changes in another thread, and we use that for synchronization. And I'll hopefully get to do an example of two of that in a little bit. Usually it's a good idea to use the pthreads synchronization stuff, but it's not always the fastest. And we'll hopefully get to play with some lock-free data structures later on in the semester. And that's all ad hoc synchronization. Okay, so for a lock, there's basically the acquisition. It's called, in the Pthreads API, it's called Pthread mutex lock or Pthread spin lock. Those are the two lock types that are available. We're going to talk quite a bit about lock implementations later on, but yep.
Where do futexes come?
Futexes are part of mutex. Yeah. Right. Okay. So there's the lock. There's the acquire. It's actually called lock in the Pthreads nomenclature, and then there's the release. Like the more formal terms, I guess, is acquire a lock and release a lock. In Pthread, they call it Pthread mutex unlock, spin lock, unlock. Right. So it gets a little gets a little strange with the lock, but okay. All right. So for the purpose of our discussion right now, the difference between a mutex and a spin lock is that if you try to acquire a mutex lock and the lock is already taken, then your thread will go to sleep. It won't use the CPU anymore. It ends up in a wait queue in the kernel, and some other process gets to use the, sorry, not process, your thread. Some other thread or process gets to use the core. Whereas with a spin lock, you're just checking a variable in a loop over and over to see, did it become a 0? Because a 1 means it's taken, so you wait until it becomes a 0 and then you go, essentially. There's some atomic instructions involved to make it safe, and we'll look at that later, but the main message is mutex goes to sleep and spin lock hogs the CPU. Of course, with a spin lock, you could be spinning for 10 milliseconds, and then you go to sleep anyway, because then a timer interrupt goes off and the kernel will decide that someone else deserves to have the CPU. Okay, so the sort of the semantics of lock here is you acquire a lock only when no one else has acquired it. So if someone else holds the lock at the moment, this Pthread mutex lock or spin lock, they both will just wait. They won't return until the lock is yours. So it's a blocking function. There's an alternative. It's called mutex try-lock. So there, for a try-lock, it'll see, oh, it's taken. Sorry, return a -1 or something, saying you didn't get the lock. It's rare that you would ever want to use those. generally, the whole point of the lock is to start a critical section, to run some code that must run single-threaded, and with a try lock, yeah, under some weird circumstances you might want to use that sort of thing. But usually you would have to have a while loop around it anyway. Okay, so a critical section is a piece of code that runs single-threaded per lock. Right, so it goes acquire critical section, release lock. All right, so anything can go in a critical section. It's just arbitrary instructions, anything at all. What's special here is you acquire a specific lock, and anyone else who also needs to run single-threaded this critical section or some other critical section, they need to run single-threaded sort of with respect to your code. They would have to use the same lock. So in the sense of the global interpreter lock in Python, there's only the one. So any piece of code that acquires a lock, well, so this is why I'm a little confused, because it's single-threaded anyway, but I think the global interpreter lock probably is used in the implementation of Python and not exposed to the user in Python. I'm not much of a Python programmer. So you would probably have perhaps 1 or 2 threads in Python that deal with network traffic and prepare things for the user program, which runs on one thread. And then they would have a big fat lock to protect any critical sections. Yeah.
When you acquire your lock and you're in your critical section, is there any like guideline for which core that code will actually run in, or is it just kind of arbitrary against all of the?
Generally speaking, your code will continue running on the core that you were running on before.
Okay, nice. Yeah, I was just thinking maybe of different speeds and different cores or something.
Oh, no, there's, these are they're not really, the OS doesn't really get involved. And so, with a mutex, the OS has to get involved because you're falling asleep. And that's, there was a reference to Pthreads. There's a system call called Pthreads in Linux at least. There must be equivalents in Windows and Solaris, where a lock implementation can ask the OS to do part of the work of the lock. So you might say, oh, I tried to acquire this lock, all right? But it's taken. So now you tell the OS, put me to sleep if the lock is still taken by the time you get this message, right? Because it could be that the lock became available and then you should go immediately back to what you were doing. Correct lock implementations is really hairy. And the same is true for all sort of synchronization code. It was best to avoid, except perhaps in this class. Okay, so yeah, so the point here I'm trying to make is that there's a specific lock, and you might have more than one critical section running in different parts of the code. If they use the same lock, then only one of those critical sections can run at any given time, because acquire blocks until the lock is released. That's all there is to it. You could imagine acquiring more than one lock. You require one at a time, generally speaking, so you could do another one in here if you want. If you start acquiring more than one lock, then you run the risk of deadlock. I think you may have encountered that in the past, so we'll skip it for now. This is a performance class, not a correctness class. Okay, so anyway. So now if we have more than one lock, let's see, let's back up. If we have only one lock, then we can only run critical sections on one core at any given time, right? It becomes single-threaded. So if you spend a lot of time in your critical sections, even if you run 64 threads on your 64-thread machine, but you have big critical sections, they're all using one lock, well, they're all sitting there taking turns waiting for the lock. So your machine isn't really being kept busy. The only way to make this go faster is to either remove the lock which can work sometimes, but usually that will cause race conditions instead. Or to try to introduce more locks so that different parts or different CPUs can use different locks at the same time. So one example might be in a hash table. Say you're wanting to insert something into a hash table. You could imagine having one big lock on the whole hash table, but then every time one of your cores tries to access the hash table, they have to grab the big lock. And so now the hash table becomes single-threaded and everything stuff. Or you can put a lock on every bucket in the hash table, in which case, hopefully you have many buckets. And then as long as the cores aren't trying to access the same bucket, they can continue to operate independently. And that's sort of a standard way of getting to more concurrency in a locking program. This is called fine-grained locking. So coarse grain being one big lock for the whole hash table, fine grain being lots of them. As long as you have more locks than you have threads, and they don't all try to use the same one, of course, usually you're fine. At least at the high level. Of course, we're going to look at what actually happens in fine-grained locking too, and how you can make that go a little faster. Okay, were there any other questions on just the semantics of locks? Okay, so one very important piece to remember is that the critical section is usually working on some shared memory object. Like a global variable, a global array, something like that. So just because you're acquiring a lock before you access the global array doesn't mean it's safe. It's only safe if every access to that global variable is protected by the same lock. Right? So the OS doesn't know anything about this lock acquisition, generally speaking. The language doesn't know anything about it. It's all just up to you. It's some logic that you introduce. Okay, so that's for mutual exclusion. Mutual exclusion, basically meaning one at a time. And then we had barriers. Barriers are really handy for, so mutual exclusion is one kind of synchronization. It doesn't enforce an order, but it makes sure that they're not at the same time. That's a kind of a synchronization constraint. Barrier is different. This enforces order. So the only function is called, other than initialization, it's called wait. And you say the size of the barrier. I don't know if size is the right term, but it's an integer between 1 and very large. Sorry, that's not where you say it. We need to worry about the initialization here. That's how it goes, of course. Stop me when I make mistakes like that. Okay, so for a barrier, you could think of it as a wall. Right? We put up a wall, and then it's of a certain size, and then you start having threads that come waiting for this barrier to fall. So they stand there and maybe they lean against the wall, right? And when you have size threads leaning against the wall, it falls over and then you can go. It's the general idea. And then it's fine, now it's back up again. Like everyone ran past and the barrier comes back up, and next time whoever's waiting has to wait until you reach the size number again. Implementing barriers is really hairy, but using them is actually super simple. So that happens before edge that you get out of a barrier is that all the operations of all the threads that call barrier wait, everything before the barrier wait across all threads happens before everything that's after the barrier. So it's total synchronization of all callers to the barrier, but Of course, you could have other threads running at the same time, and they're completely unaffected by this. Okay, and then there's a condition variable. And this one is kind of difficult to use. There's a couple of simple mistakes that are common to make, so we'll just try to avoid that. So there's initialization, which we can skip, and then we have pthread cond wait, and it takes a variable, condition variable, which is a specific type, right? It's pthread cond t is the condition variable, and then it takes a lock. So the semantics here is pthread cond wait sleeps, like it doesn't return until someone signals you. Signals the variable, or until some other random event happens. That's the unfortunate part. So pthread cond wait is supposed to wait until you get a signal on this condition variable, but then maybe something else unfortunate happens and you just wake up anyway. It's actually, that's the standard. That's how it should be. There's one more thing. You're supposed to hold a lock when you start waiting. Cond wait will release that lock, and then you're guaranteed that you're holding it again by the time you come back. So let's see an example where we might want to use this. So maybe we have thread 1, thread 2. Okay. So we're working on some shared data structure. And let's see. Oh yeah, okay. It's a sort of a communication data structure. I put something in this data structure to make a request, and then I wait for a response to come back. So of course, in order to write to this data structure, I have to acquire a lock on it. So write request. And now I need to wait until the response is written within the same data structure. Of course, I could release the lock, but that's actually not ideal. It'd be much better if we start waiting sort of while holding the lock. So we use a cond wait for a condition variable, which is declared separately. I should do that actually. And then lock. So now, while I'm waiting, the lock is released, so the other thread can start looking for, let's see, we go like this. Oops, sorry. Okay, maybe I should be a little more formal here. We'll do if request, serve the request, signal. Yeah, that'll work. Yep.
You're just, I have this written here. So this condition variable, it actually has to be declared before you start with threads, right? Like so both threads need to access it. So wouldn't it have to be like declared in whatever starting both threads?
I mean, so it can be a global variable,
Yeah.
or it could be part of a data structure that both threads have a reference to. It's not really that important, but you're right. It can't be a local variable like this. That's not good. I'll put it here. Thanks. Okay, so let's see. read response. All right. So we have a relatively complex system here. We have two threads that communicate through a shared data structure. Generally speaking, that's the only way that threads can communicate anyway. So that's fine. In this case, we're using condition variables. Maybe we could have done this with barriers. Probably would be awkward. So you could imagine many threads wanting to send requests, and there's one thread that's serving requests. It's all going through this shared data structure. Of course, you want to modify this data structure to write a request into it. Well, then you're going to have to acquire a lock on the data structure first. Otherwise, we'll have race conditions and everything will get random. Okay, so we write our request, and then we start waiting for a signal to this condition variable. By passing in this lock, we're now guaranteed that by the time we come back, we're still holding the lock, which is beautiful. Otherwise, what could happen, I suppose, is you try to acquire the lock and then the response has gone. Some other thread receives a response instead. Maybe something like that. Yeah, so it's not always clear that you want that you would want to that it's safe to release a lock over here, or it's not always safe that you would come back from here and then try to acquire a lock. Maybe you can't acquire the lock; someone else has it. So anyway, we're not waking up until we actually hold the lock. That's the general idea. And down here, we're acquiring a lock to see if there's a request in there. We serve the request. Because we're holding the lock, no one else can write to this data structure. That's safe. And then we send a signal to wake up this other thread. It won't wake up quite yet. Right. Anyone know why? And because it slept. Well, so we're waking it up with a signal, so it should come back, right? Exactly. We're still holding the lock. The condition wait doesn't return until the lock is held again. Okay. There's actually one thing that's wrong here. It's a very common mistake to make. No, it's okay actually. You can signal before or after the lock. That doesn't matter.
So, according to this piece of code, there's one thread which is acquiring the lock and then waiting on it, and then there's another thread which is also trying to acquire a lock and then signaling on the same condition variable.
Yeah. So this is actually this is part of the desired semantics here. Acquire the lock, and then while you're waiting, the lock is gone, like is released temporarily, right? But the problem here is this const wait can return spuriously as well, right? Ideally, you want it to only return when you get a signal, but it can also return other times. You can't trust this thing. It's just kind of a, it has nothing to do with the condition. That's the thing. I don't know why it's called a condition variable. There's no condition here. There's no like, oh, if this is true or anything like that. It's just like, hey, wake me up, right? Or wake you up. So what you have to do is you always have to have a while not response ready. It's always like this. We could maybe write it this way. So a couple of things could happen. You could write, without this loop here, a couple of things could happen. You could write the request, and now the other thread gets to run immediately, just out of kind of random ordering of events. So it sees there's a request and serves the request, writes a response. And this is before, and then signals, before we even get to run this const wait. That's something that easily could happen, and now the signal is sent already, and then we start waiting after the signal was sent. So we lose the signal, and we'll wait forever.
Yeah, can it not do that because it has to acquire the lock, and it can't acquire a lock until you condition Did you say that you released the lock convoy?
Okay, good. Let's see. Very good. Yep, you're absolutely right in this case. I think now I'm trying to think. So this is all happening because we have this lock around our whole shared data structure. Probably that can't happen. And so, all right, good eye. Another thing that could happen, a thing that could happen, because the other one couldn't. Now, assuming we're operating properly with locks around the request-response data structure, is we might return early. So we're in this wait, and then we return before we actually get a signal. What happened to it? Oh, there it is. And this will happen, I think the main case where it happens is actually when you have user, like delivery of OS signals, different kind of signal here, but like the interrupt from a control C or SIG pipe or a SIG kill or any one of those OS signals. If I recall correctly, that's a common place where conv wait will return. Otherwise, it makes for potentially infinitely large stacks on the user side. Anyway, you have to live with the fact that it can, sometimes it can return when you didn't get a signal yet. So in that case, and generally in other cases too, you'll want to have a loop like this. So you're always checking a condition first, and if the condition isn't true yet, then you do a condition wait. So the wait is not for, this variable has nothing to do with condition, other than, I mean, it's vaguely associated with the condition perhaps, but it's only there to kind of decide how long we wait. The condition that we're checking is separate, and it's in a while loop around the conv wait. So what's nice about this is that even if we were to remove this conv wait, the code would still work. Hopefully. Well, in this case, it wouldn't, because we have this lock here, so it wouldn't be able to get in. Yeah, it wouldn't work at all in this case. In some cases, your conv wait will, all it'll do is put the thread to sleep for a while, and make the whole program more efficient, but perhaps not more correct. Yeah.
This thread 2 exists because of some interrupt, will it automatically release the lock? Because if not, then the first thread will just keep on waiting for it.
Oh, okay. So let's see. So if thread 2 does what? If it exits?
Yeah, this thread is actually go to the control C.
Yeah. So, all right. So I probably shouldn't have mentioned those signals, but yeah. So if you hit Control C, this is delivered to the process. The default handler will exit the whole process, all threads. Everything's gone. Assuming we have the default handler, we don't need to worry about it. If you happen to have a handler that kills this thread, that kills thread 2 only, right? Then yeah, you would end up with this thread 1 waiting forever. But that's a bug in your code. There's no automatic release of locks. The OS doesn't know about locks, and so yeah. Okay, so that's condition variables and an ad hoc synchronization. Let me show you one very simple example. Would be we go like this: while not start. Right. So in one of the threads, you run this, and then in the other thread, you set start to 1, and then this one goes. It's a little bit of a, it's definitely some sort of synchronization operation. It's a little shady. That's why it's called ad hoc synchronization. One way that it's shady is if start isn't volatile, the compiler will probably optimize it out. Right? So, or at least it'll be a while true while not. This one is always 0. So, I mean, it was 0 initially, so the compiler will figure it's always going to be 0 because it's not a volatile, and so it'll loop forever. So whenever you're doing ad hoc synchronization, you have to be a little extra careful. Hopefully we'll get to see some cool examples of that later on. Now I wanted to show you a little bit of what happens when you, like what's actually going on. So I wrote sort of a template program that only does timing. So the point here is we're starting up, okay, so this one. Read timestamp counter, and the P is I don't know, it could be for processor ID perhaps. So you get this more or less cycle exact time. So the timestamp counter goes up by 1 every cycle. That's the general idea. This with the P is a serializing instruction without. It runs in parallel with all these other 100 instructions, so it's a little less precise. So of course, it's a much faster if you do it that way. The serializing, all the instructions before this have to finish, get retired before you get to take the time. And so that prevents speculation of anything in front of it, and it just goes a lot slower. But anyway, it's precise and we like it. This is an alternative to say, get time of day. Get time of day will give you microseconds, sometimes nanoseconds. This one gives us cycles. It translates to a single instruction. This is RDT-SCP. RDT-SCP, yeah. It's an assembly instruction. Read timestamp counter. Okay, so I'm timing before I do anything, and then I start a whole bunch of threads, and then I wait for all those threads to finish, and we print out a time from inside of the thread. So basically, all every thread does is see what time is it, right? And then we're done. So the question now is, how long was it between, and here it is, between when we started starting threads and all these threads actually got going? That's the question. And to what extent can we control that? We'll try to experiment a little bit with that. Before I do that, any best guesses? How many cycles will it be before the first child starts? Yeah, let's start with that. First child. Thousand cycles, okay, that's a good start. What do you base it on? Or it's just a guess? Just a guess. Yeah. Any other guesses? Yeah, I'll make a guess. 1 billion? It's too high, right?
Yeah.
That's like a half a second. What is he talking about? All right. Any other thoughts? 1,000 seems relatively low, too. 500 million. Okay. Yeah. All right. That's still a quarter second. So, when you start threads, if it took a quarter second to start a thread, it would be kind of annoying. All right. So that's probably not it. 100,000 cycles. Yeah, maybe something like this. I don't remember, but I do have the code. So why don't we run it? Where did Emacs go? It just crashed. Okay. Okay. I should ask people to leave it alone. Let me just do that. Okay. Thread timing. All right. Okay. So it's upset because these two things belong in a library called libpthread, and so you need to link with that. So, all right. So let's run it. See what comes out. Okay. So we have a thread ID. And this is printed out in a synchronous for loop here, right? Single-threaded for loop. So the thread ID will always be in order.
Professor?
Yeah?
Can you increase the font size?
Yes. Thank you. Better? Okay. This is the processor that it was running on. There's 64 processors in the machine. So I started 63 of them. I didn't want to conflict with the main thread. So we started 63 of them, and they seem to be pretty much all over the place. Right? But some of them run on the same CPU. These are back-to-back threads, and they run on the same CPU, even though they're spare CPUs. Okay? And then, when did they start? Here's 1 million cycles. 1.8. Toward the bottom, 14 million. All right. So it's pretty much all over the place. But it's not 1 billion, so that's good. So if you're starting these threads, you're starting a bunch of threads and you want them all to be working on something together, the first one starts 1 million cycles in, and the last one starts 14 million cycles in. So chances are they won't be working on the same thing. Like you'll have one of them working and then the other one. Sometimes that doesn't matter, but if we're measuring performance, it does matter. So I thought, why don't we try to see if we can make that a little tighter? Can we get them? How closely can we get them to actually collect the same timestamp? Right? That's what I would ideally like to see. So, any ideas? Yeah.
Barrier.
Let's use a barrier. And now I need a size. It'll be max thread plus 1. Right? So I'll do a here. And then right after we take the before time. Oh, no. Now we can take the time a little differently. Right. So now we get to create the threads independently. You could imagine that there's quite a bit of OS overhead here in creating a thread. So now we can skip that, which is nice, because we're asking all of the threads to wait. Maybe they'll start up, they're spinning maybe, or at least they're waiting one way or another. And then they collect the time right after the parent pushes down the barrier. Okay. So we take the time on the parent, we take the time before. So that should be pretty tight. See how that goes. Anyone want to make a guess?
14 million?
14 million, okay, so like this one. Yeah. So we're better, right? 143. It's roughly increasing. It's not completely increasing, right? This one started a lot faster than the one before, but roughly speaking, it's increasing. Why aren't they just increasing like one after another? Like why did this thread take so much longer than this thread to start? And this one started long after the one that got started after. What's going on there? Yeah.
This is the only process in the CPU.
true. There's a whole bunch of processes here that maybe could have a use for the CPU on some occasion. So that's one good argument. But I think the main thing going on here is probably that these threads are all asleep. They're sitting in the kernel. The kernel isn't actually running this right now. It's doing something else. And so at some point, a signal, some sort of signal, needs to make it from one core to all the other cores so that they realize that things have changed. And it all depends on the state of the target CPU at the moment. So in your case, yeah, it could be that they were running, that CPU was running some other process, and we're not going to do anything about the lock or the barrier in this process until that process is done. So that's one very good reason. There's just all sorts of noise going on in the machine, and you can't trust it. I was talking to a guy from Argonne the other day. He happens to be a neighbor. He controls he writes the embedded system code for the the circular accelerator there to direct the whatever proton beams or whatnot.
APS?
What's that?
Yeah.
So he wrote the old one, and that's the APS, I think. And now they're doing a new one, so he's working on that one. But anyway, his point is they need to, basically, they have all these detectors around the circle, and they need to change some magnet on this detector based on what the previous detector saw. But this particle travels at the speed of light. So you don't have a whole lot of time. In fact, you have about 3 microseconds. And that's not enough time to even like send the stuff. So it's really tight even if you go one time around. So they use one cycle old data, and even then it's like super tight timing. And so they don't run an OS, because then you get shit like this. Right? So they run a specific, just an embedded board with no OS, just their program running on it, no interrupts, no nothing. And then they can control their accelerators.
Are they using multiple boards per like segment that they need that?
They have some DSP on each one of those. Like it's a whole distributed thing. You can't have it centralized, because then it's an extra round trip and you've lost it. So anyway, that was a kind of a fun chat. Okay, so that's barriers. But can we do better than barriers?
I have a question.
Yeah.
So, if you look at it, one of the threads was like 100,000 cycles.
Uh-huh.
The first one. But in the previous example, when there was no barrier, at that point, everyone started at 900,000.
Right.
So why did one start so much sooner than before?
Yeah, so I think that's because we're taking the time now after the creation of the thread. Right? Before we had no choice. We couldn't very well take the before time after we started them all. We'd have a bunch of negative times. Okay, but so I think we don't have time for the condition variable, but we can do an ad hoc, because that's a lot easier. So we could do it like this. In fact, I already have something called start here. So we could say, instead of the barrier, like that, and then, all right, what do you think?
Awful for start.
Excellent. Okay, so now this is ad hoc synchronization. We sort of know that after, like, it's gonna stay 0 until we write something here. So you have a happens before edge, almost. But if we were to do some other things around here, like if I was to write, say, write a value over here, and then look for that value up here, it's not clear that whatever I wrote would be visible over there. It's not a strict happens before sort of situation. In order to get that, you really need to use atomic operations or an msync instruction that can also provide that sort of guarantee. We'll look at that in more detail later, but right now it doesn't actually matter. It's okay to be sloppy, because it's going to be 1 eventually. As long as it's volatile, the compiler will keep reading it. It doesn't matter if it arrives a little bit later. It'll still be faster than trying to use an atomic operation. So let's see what what we get. Right. Okay, so now we're starting to see sort of the limitations of the machine. I think it's not quite right still. It should be faster than this, but so 2,000 cycles, 1,000 cycles, something like that. Looks like what we're having. But then sometimes it's way off because, well, some other process needed a CPU, perhaps. So I think the main lesson here is you really have no idea which one's running next unless you have synchronization operations in between. I wanted to try a couple more things here, see if we can make a fun effect. See if this makes any difference. No difference. And let's see. I think it's taking too long, this stuff, so trying to figure out if it's attribute aligned. Damn it. I think it goes like this. And if it doesn't go like this, we'll do it next time.
I think the parentheses are wrong again.
Are they? Oh, it should be one more. Okay. See if that makes a difference. Nope, doesn't make a difference. All right, so yeah, in my experience, we should be able to get down to about 1,000 for them. But that's sort of the granularity that you can expect of communication, like timing between CPUs. So if one CPU wants to tell another CPU to do something, we're really low down there now. We're just making one write. And so there isn't much else you can do to get more precise than that. So basically, these CPUs, they all run their own show. And then sometimes you can have a little bit of communication between them. That's what's going on. Okay, I had promised a new homework. I apologize. Still not done. I ran through a whole bunch of different examples. I'm trying to find a really interesting data structure that we can work with for a few weeks, but yeah, so far no luck. But I think I have a good candidate, so maybe tonight or tomorrow. All right. Have a good one. See you later.